Morning. My name is Pieter Kempeneers. I'm with the Joint Research Center of the European Commission in Ispra in Italy, and I'm going to give a talk on pyjeo. Well, it's both a talk and more like an exercise on using pyjeo in on the cluster on the HPC system SURF. And how to do that. More in particular, there will be two exercises. We'll go a bit into the parallelization process, how to do it in two different ways. But first, a few words on pyjeo. I know that I've been giving similar things last year, so maybe some of you might already be familiar, but I think it's needed in order to for everyone of you to understand what we're doing in the exercise. I think it's needed that we go through a bit of the basic concept of the pyjeo package. pyjeo actually is a Python library that we developed internally in the JRC, and it's a spin-off, let's say a continuation of a C++ library I developed quite some time ago for my PhD on image processing that was developed in C++. And now I hear from in the previous talk that we should move back again from Python to C++. So I went from C++. I made a wrapper to Python. Maybe I have to wrap again and go to C++. But no, I think it's been a really nice experience. I really like programming C++, but I do see the added value of going to Python. There's so much available and new libraries that are out there, open source also, that really I can benefit from them, and we'll see a bit how that's done in a moment. Yeah, let's start. I've put here a timetable, but I think it's a bit useless because I'm not sure how it will go, and maybe just maybe as a content I'll try to stick to it more or less, but I'll give an introduction on the installation and on the design, on the data model, how to use it. So I've created this Jupyter notebook. I can share it later on, but you don't have it at this moment. So I just please bear with me and see the difference. It's more like a presentation than really a code, but it's to follow the main ideas about how the pyjeo module package is built. But you can install it on your local machines. You can install it on a cluster. So we'll see also how I did it here for the SURF HPC. Oh, sorry, that's not what I want. It's the installation. It's like Giuseppe mentioned. If you're on a Windows computer, you're in bad luck because I don't provide any installation scripts. So for Windows, I do have a Docker file, so you can create a Docker image so that you can use it also on other machines. But it's merely also like when you're using on an HPC, it will be Linux anyhow. So that's not so much of a problem. So the design is when you install it, you'll have a number of modules. So you call the different modules, and I try to distinguish the different types of operations you need to do. Like there's the properties. If you want to load an image and the image is in memory in like an object, you can get some properties like the geo information or the number of columns and these type of things. Then there is input output to write images. There's geometry to do operations that are related to geometry, like extraction of polygons over rasters or other geometrical stuff like warping and so forth. Then the pixel operation, everything that is not related to the geospatial context, but that can be really operations that can be done at a pixel-based level. This is in PixOps. Then there's some neighborhood operations, morphological operations, more in particular, and some classification operations, some digital elevation model operations, and then some connected components for segmentation. Again. So let's go a bit. The documentation is written in Python, and there's an online version supported by Read the Docs that should be rather extensive, but it's still an ongoing process. You can also have inline help using the help in Python directly. So, for example, if you want to get some help on the warp, you should. I imported pyjeo as pj, so pj.geometry, because warping is a geometry function, and then calling the help will say how you use it. Then very important is the data model that is behind. So I treat an image as a 3D data cube with one dimension the number of the columns, another dimension the rows, and another dimension what I call planes. And this is typically like a temporal domain, in the dimension in the temporal domain. And then there are also bands, like spectral bands. But this is, the 3D is not for, normally you have to see like they're more or less 4-dimensional, and you can switch a bit in between, but you have this 3D data cube for X, Y, and Z, where the Z is then typically temporal dimension, and you can replicate this cube for several bands so that you have separate spaces in memory that represent these different cubes. To give an example, when I load a single band image, single band, single plane, I have just 2 dimensions like what you see here. So if I call the properties of that image, for example, these have 100 columns, 100 rows, and just a single band. So this is a single band plane image. You can have also multi-band. So if I load a multi-band GeoTIFF, I automatically have this image loaded in memory, and I can check the number of bands. In this case, there are 2. So what we have is actually not really a data cube in this case, as I mentioned, because there is no time dimension, no plane dimension. I have 2 separate bands, so this is a 2-dimensional image replicated in memory 2 times for the different spectral bands. If we go to multi-plane images, I can load the same multi-band, so 2-band image, but say I want this as a 3D data cube, not in several bands. So I can say, I want to convert it in a 3D object by saying band to plane. I want to convert my bands into planes, and I have a 3D object in this case because I have a single band but 2 different planes. So it's just a way of the data model, how the data model is built, and you have this 3D, as you see here on the top, a 3D data cube with 2 dimensions, 2 planes in this 3rd dimension. Of course, then you can have a multi-band and multi-plane image, so that you have a 3D image, but still in 2 different spectral bands. So, for example, if I'm, sorry. It's just, there's a delay. That's the problem. Yeah. So here you see this 3D, I have to stick here with the mic, a 3D data cube and 2 different bands. The number of X and Y in this case and Z, they must be the same for these two different bands. Otherwise, you need to create a different object. Very important, as I mentioned. So one of the main purposes of going to Python was first of all that it was more user friendly for scientists to use the package, but also to take advantage of many of the other packages that are available. So for that, it's very important that the internal data structure that I have in C++, which is just like a pointer with a data array, that I could go easily from this internal memory structure to other data sets, other packages that are available. Like most of them are relying on NumPy or like Xarray, or so you can, once you have done the trick to go to a NumPy array from your C++ data array, you can have access to many of the other packages. So the first thing to do was to make it compatible with NumPy arrays using the C++ API of NumPy. And from that moment, you have everything at your fingertips from the other packages as well. So that was really a big benefit. So to give an example, when we use Xarray, when we import it and I load a netcdf that is a multi-band, multi-plane image in pyjeo speak, let's say, I have, this is the Xarray representation. So it's really an Xarray, this X. But I can go both ways. I can create a gem object from pyjeo by using this pyj xarray to gem, giving the X as an argument, and I have my gem object where it's multi-plane and also multi-band, as you see here. And I keep also, like similar what Xarray is doing. Xarray has all the information of the georeference, the names of the bands, the name of this temporal dimension. It has all this information. I have this information also in that object, and I call that like the dimension of the object. Here you see the plane has two time variables and one band dimension with variables B1 and B2 for the two spectral bands. Then we go a bit more in detail. This we will use during the first exercise. So we have still the same gem object being a two-band image with multiple time acquisitions, and I can calculate the NDVI, mentioning what is the band name of the red band, what is the band name for NIR, and I want to name this new dimension NDVI. In this case, the gem object will be overwritten. There will be only it will be a reduction in the spectral dimension. The bands B1 and B2 will cease to exist. There will be just a new band, a single band image, multi-temporal, with the name NDVI. So you see here there's a band and still two different planes for the times. You could also append, like having a third band instead of getting rid of the red and the near band. You could add the band by having a different option, say add band is true, and then you have a three-band multi-dimensional, multi-temporal image as well. But in this case, it was a reduction of the spectral dimension.
Peter, yes. Sorry, one question.
Yes.
Why we don't see here B1 and B2 as bands? Or...
Yes. So that's because I was saying here that I wanted, if I would have said here that band is true, we would have it. Now it was already, the damage has been done. I got rid of the, so let me open it again. Here I have B1 and B2. If I now calculate NDVI, I have still B1 and B2 and NVI because I added the band. Sometimes you want to get rid of them and then you don't want to add it. In this case, I wanted to. So this was going from an X-ray to a GIM object to be able to use all the functions of pyjeo. The other way around is also possible. So suppose you have a GIM object and you want to create an X-ray so that you can use the full functionality of X-ray, then you just use the representation of X-ray of the GIM. So you say gim.xr, and it will provide you the X-ray, a real X-ray actually of my image. And you see those three bands here again as real data variables, and the spatial ref, everything should be available as you would need also from a normal X-ray. Yes, please.
Is it okay? Is it okay if you pose the questions or your?
All yours, yeah,
okay,
please.
Thanks. So I just want to clarify the concept because I think it's quite important.
Yes.
So basically the planes and the X and Y, they end up as a coordinate. So you treat them as a coordinate. So that's why plane is only reserved for a temporal dimension, and all the additional bands and computations, they're kept as bands. Yeah, so this is like a separate.
Yeah, this is true. This is very much correct. This is especially true if I've made this choice to for going back and forth from an X-ray. Of course, once you're in the GIM. In the pyjeo world only, it doesn't matter if the planes are the temporal dimension or you can switch around the temporal and the spectral dimension because it's just a dimension. But in order to read and to interpret those things correctly for X-ray, going back and forth to X-ray, I made the choice to make the planes in temporal dimension and the bands in the spectral dimension as the data variables. Yeah. Yeah. For those of you not familiar maybe with how in X-ray uses data sets and data arrays, what's the difference? So a data set has all the named variables as you see here on top. If you go and really fetch a data variable like the B1, you can convert this data set into a data array, and then you have slowly, I'm not sure if. Okay, so here you have a data array. So it's no longer a named array. And you have your data array as you see. So it's a different representation as we saw above. So here we have a time dimension, an X and a Y, but we don't have this dimension for B1 because we are already in this B1 as a real data array. And then you can even go further into the NumPy representation. So it's a bit similar as I was doing in pyjeo, that you can have the NumPy of my data. In X-ray you have also, because there it's even closer to NumPy, I believe. So you can really go to the NumPy representation of that. So you have the similar thing in X-rays. If you go to data, you can really go up to a NumPy array. A similar thing is existing for the GIM object of pyjeo. Instead of doing gim.xr for the X-array, I can say I want my NumPy array from my GIM, and you have here the same NumPy array. In this case, you still, because my GIM is multi-temporal and multi-dimensional for the spectral bands, I need to select one spectral band. So the spectral band in this case is my first band, and I select. I could have used the name here as well, the B1 or B2, but so this is really the same as I was doing above for the X-ray, going to the B1, having the NumPy array. I can do that for the GIM object as well, and then you can use any function that is operating on a NumPy array. you can access some of the elements. So let's load that same multi-band again. But here you see I'm using this band to plane is true. So I will directly load that multi-band image into a multi-plane image. And I can use similar operations or behind the scenes. Of course, there's some other tricks, but you can use the same typology as you were using for NumPy arrays to select some of the bands. Like this is the first band and all X and Y. So you get this type of an image. You can get 5 by 5 blocks of pixels by selecting the second band, because we're starting from 0 and then from 0 to 5 index like a range of X and Ys. And we have this X array. Again, here when I would omit this part here, I would just have returned the gem object, but by calling the .numpy, I have the NumPy representation. I can easily plot it in this way. Because if I would do this, I would just get a gem object, so it doesn't give me any more info. I mean, it doesn't show me the real values. So if I go to the NumPy representation, it shows me actually the values. Then, yes, please. Yeah.
One more question. So what is happening in a situation when we have overlapping images? So is it during the import, is it resolved, or for example, when we have several images, does it doing a mosaicing immediate on the fly, or how is this handled?
Yeah, that's a good question. So here you have to bear in mind that first of all, they are the images as they are represented as directly in memory. They have to fit into the same blocks. So it's not that one image is shifted towards another. So they have to get the same dimension in X and Y when loading them. So it's typically like a GeoTIFF image that you would load, and then you have the time dimension in as overlapping images, but they overlap 100%. It's not like partially overlapping. Then the compositing can be done at a later stage by doing a reduction. So you would typically call the geometry module, and in geometry there is a geometry.reduce, and then you can define several reduction methods, which is like the compositing steps that you can select the maximum or the minimum or a customized type of reduction step.
So the data has to be prepared basically before loading.
Yeah. It's not that. I mean, it's not that you load a bunch of images that are not and then it is all taken care of. No. So for that, because also there, I sometimes now already I have the impression that I'm reinventing wheels, but of course I was reinventing the wheels quite some years ago. If I would start all over, it would of course be quite different. But I try to limit it at least now as much as possible. So for now, if I have this typically example of when I need to read a data cube from a number of Sentinel images that are in the catalog, I will not reinvent that wheel. I will make sure we at the JRC, we have all our Sentinel images stack compliant. So we have a stack catalog with an API. We can read those with the existing software that is already available. So I use typically ODC stack or stack, where I just provide the search items to go through the catalog. And then there's that available software already that is doing this type of creating the cube for me in an X-ray. And then I can stay in the X-ray world, or can easily convert it to a pyjeo object. So I leave it up to people that have done that work already.
There is also GeoWombat
Yeah.
This is also Python package, but this is mostly dedicated for satellite images, so one can make mosaicing and like mini cubing with GeoWombat. Yeah, so it's a bit tricky to use it, but yeah, I think it's a nice tool. Yeah, and it also provides it to X-arrays. Yeah. Yeah. GeoWombat. Wombat, yeah, like animal, Australian animal, yeah.
No, just a comment on top of it. Of course, it makes a lot of sense. So basically, here you are just assuming that the cube it's already created and the data it's a kind of already regularized. So in what we do at OpenGeoHub, basically we prepared everything in advance, and you can even use like VRTs. So for example, if you have like the Sentinel data, you can prepare it as a VRT. And if you want to combine with some, I don't know, 1 kilometer data or temporal climate data, you can have a VRT that you basically, if it's in the same projection, you can kind of downscale the pixel for 10 meter if it match with the Sentinel grid, and you define kind of on the fly the reprojection approach. So if you have like the TIFF files in a kind of gridded, already predefined, you can do some on-the-fly operations with the VRT, and it's quite efficient. And for example, as far as understood, if we point for the gene object, it will just read in memory.
Yeah, very good point. So indeed here, instead of opening a TIFF file, you can immediately open a VRT file, because of course behind under the hood, like in most packages, there's also always GDAL behind. So if the file format is supported by GDAL, I could also open it like the VRT, which I do very often. So that's a very good point indeed. Maybe some additional words on methods and functions. I try to in order to optimize the memory footprint, I try to not to duplicate data too much. So what you often see in other packages, like for example, take the example of NumPy. Most of the time, without doing anything special, the data is duplicated. So whenever you call a function in NumPy, there's a new NumPy returned. There are some tricks also there to avoid it. If you, for example, the naming is sometimes different, but you can sometimes it's copy is false, or in place is true, or this type of things. They handle it in that way. What in pyjeo we have chosen for a different approach, separating between methods and functions. So those of you maybe not familiar with object-oriented programming, a method is called directly on an object. So Jim is my object, let's say, is my image. If I call a function like, let's open this image here again, 2 bands. I can do geometry crop band. I want to select only a single band, and this is a function. This is not a member function. This is really a function where I call the package pyjeo.geometry.cropBand, and I give as an argument my object and the band index, the first band in this case, to select. And in that case, it's the NumPy way of doing things. I return a new Jim object. So because my Jim, at the end of this operation, my Jim is still existing, and I have a new object, Jim cropped. However, and my Jim is still existing, has still the 2 bands. Jim is unaltered. But in a method type of case, if I have 2 bands, if I call this crop band from the geometry module directly on my gym object. So here I don't have pj dot. I have my gym object on which I call a crop band function, a member function in this case, directly on my gym. My gym is really altered. So this is really in place because now I have only a single band image, which is, it has been cropped. So in this case, you control the way, if you no longer need your gym object, you get rid of it and you reduce your memory footprint. And so this is also, I think it's important, especially for those that are newer to programming. Initially, I still come from an age where memory was quite precious. So I'm more vulnerable to when I program to see the things. But sometimes when you have like all these nice packages in Xarray and NumPy, and it's tempting just to call the methods there and to keep all your old members available and just hoping that the garbage collection will do its job. But most of the case, it's doing only it at a later stage or maybe too late. So yeah, I think it's a good practice to think of it, that you don't duplicate it when it's not needed, especially if you want to keep things as like fast and efficient, that you want to do as much as possible in memory. So what else? So there, apart from these member functions and real functions, where you can define how your memory footprint is affected, there's also two different functions you can use. You can use a built-in functions that are really implemented in pyjeo. But again, here, try to avoid as much as possible to reinvent the wheel. So if there's a function available, and of course, I'm not going to get rid of the function I already created in the past, but still, if I don't need to create something new, I try to use existing functions. But one of the really important functions that are there is reduction, so doing composites. So here I can create a median composite by calling the reduce plane median. But I also have some from the past, some filtering, but then I see, okay, now there's so much available in already like filtering operations. Why should I try to use my own? And there, I think it's just better off using the available, because there's been much better and brighter people programming already on these issues. So let's use those. And for example, there's a trick I can do if I want to. So here again, trying to limit as much as possible the memory footprint. But let's say I want to call from the ND image from SciPy the Gaussian filter operating on a NumPy array. So I need a NumPy array here. But I have my gym, so I call the NumPy representation. By the way, there's no memory copy here. It's just going directly to the same memory of my gym object, but then seeing it as a NumPy array. There's no duplication. I can call the Gaussian filter with a standard deviation of 2 or 2 times the standard deviation, and I will reintroduce it in the same gym object by calling, because the result will be a NumPy object, and I want my gym object, so I can call the gym object here, getting the NumPy representation, and say I want all values of my NumPy representation to be filled in with the result of this ND image Gaussian filter. So there's of course there will be some duplication behind the scenes, but as little as possible. And after this operation, the gym will just have the real result of that filtering operation, and not like a duplication. So that's a way of using third-party libraries. Sometimes when you read a GeoTIFF image, the dimensions are not named, and it's sometimes very convenient to have those names, especially if you want to go to an X-array where there's named dimension. And when you read the GeoTIFF, sometimes it's not the case, or mostly it's not the case. So what you can do is to let me go. like here, in this case, if I call X-array, I have to fall back to, because I'm reading this directly from a geotiff, where the dimensions are unnamed. So if I convert that to an X-array, I have to get some names, and I just call the names like an index 0, 1, 2, 3, 4. I have a time, but the times are just T0, T1, T2, because I don't have the real information in that geotiff. But I can fix it manually. Say I want to name these dimensions manually. Say, okay, I set the properties, the dimension, and I call the names January to August and September and November, December, and my band is, for example, an NDVI. Once I do this, and if I then convert it to an X-ray, I have the real proper dimensions as it should be, with an NDVI data variable name and so forth. And of course, here again, we use the great capabilities of X-ray to plot. I don't need to plot to create any plotting functions in my library, because if I convert it to an X-ray, I can use already the plotting functions that are there. So this ends the introductory part. Just what I want you to retain here is I want you to be aware of the enormous amount of libraries that are available, and also offer with pyjeo. If it's useful, you can use whatever you want. But if it's not useful, you can even just, I mean, if even there's a single thing that is useful, you just use it, and then you convert it to another representation and use all the other libraries. Or the opposite, you use another library, you want to use just one single function here, and you can go back and forth. And with that, I'm happy to answer any questions if there are, and otherwise we move to the exercises.
Yes, Peter.
Yeah.
And when you do, for example, to gim2.np or gim.xri, there are not duplication in the data, isn't it?
Yeah, depends. There, here again, I have the sometimes it's whenever possible I do it. For example, if I do gim.xr, there is no duplication. If I do gim.np, there is no duplication in the same mindset as the member function. However, I can also do pj.np to gim. Then it's a functional way, and I do a real copy. Sometimes you want a real copy, and it has. Sometimes it's also it's because I'm getting on thin ice at some points, because I'm not really only in the NumPy world, and I had to go through in the C++, going back and forth of these. And if I don't want the duplication, and I'm using the same memory dataset, and let's say I do a gim.np, returning me a NumPy array without duplication, and I then do changing some of the real typical things like making or removing the object, like setting it to none, and then I want to use my gem again, then you're getting into trouble. So you have to be careful a bit with this. You have to know what you're doing. You're capable of shooting in your own foot, but I think it's worth, if you don't know what you're doing, to have this functionality. I'm going to grab a glass of water, and then we can go to the... Yes, please. pyjeo is to kind of stack the arrays together, or I'm not sure if it's the main strength. I think many things can do those stacking. Not only pyjeo, I think others, like in NumPy, you can do the same things. In X-ray, you can do the same things. I think it's rather a number of functions that are available, like doing type of easy reductions by just, I say, reduce the number of planes by taking the maximum. You can do the same things also in other packages, but maybe here it's maybe a bit more intuitive without programming too much. There are like the digital elevation functions. There are the segmentation function that you can use directly. I think everything is possible in any package, but sometimes it's just how familiar are you with it and how intuitive it is. So before we go to the real exercises, I think it's not bad to remind a bit of the different concepts. We have seen already most of them in the previous talks here, but allow me to get to a bit of a summarize to get it fresh in our minds. We have seen there is a difference between high performance and high throughput computing. And if it's not clear yet from the previous talks, I think it's important to realize that it's two different things, and high performance computing is typically used for jobs that are tightly coupled, and parallel applications, they really require dedicated software. So if you're not knowing what it is, you don't mind, because you won't need it, because your programs and the way of programming is really specialized. You need message passing interface, MPI, libraries for that, because we're talking about jobs running on different nodes on different computers, let's say, that need to share, to pass some information from one to the other, like because they have different memory spaces. And if I need to access some memory of some information from another job, we need to communicate between those, and this is not trivial. So this is a totally different way of computing than high throughput computing. What most of us, I think, and especially myself, are dealing with. In high throughput computing, this is much simpler in a sense from the communication aspect. The jobs are typically not at all or very loosely coupled, and very typical are the what we call embarrassingly parallel workload. You have a huge image, the whole world you want to process, but it's let's say a pixel-wise operation. You want to do to calculate the normalized different vegetation index, the NDVI of two spectral bands, the red and the near infrared band, and you can do that for every pixel. If I'm calculating this for this pixel here and for another pixel there, they don't need to know about each other. You don't need to pass any message. You can do the pixel operations on many different computers and then still merge the result at the very end. So that's two totally different things. Then another thing we also probably seen is how you can do the parallel processing. You can, in this embarrassingly parallel processing example I gave of the NDVI pixel-based operation, you can tile your image in as much as possible, even to the limit every pixel, you can send the calculation of every pixel to a different node. If you have many different cores, if you have many different cores, you could do it. It's not optimal, of course, because you have to open a very small portion of the image, and then it's already finished by the time you try to open it, and you have to close it already. So it's not optimal, but you can see there's kind of an optimum by knowing how many cores you have and how many tiles you are creating to divide it. Then there's another way of parallel processing. And by the way, we will do this in the first exercise. Another way of parallel processing is multi-core processing using a dedicated library. It's a bit similar to the MPI, the HPC here, but not really the same. But at least your programs need to be created for that. You cannot just say, okay, I'm doing multi-threading, which is what we're talking about here. I want to do multi-threading if your program doesn't support it. So, but the first one, the embarrassingly parallel processing with tiling, that is almost always possible if your application, if the problem you want to deal with is capable of doing like the pixel-based operations, for example. So we will see a second exercise where, because some of the functions that are implemented in pyjeo, they do take into account, or they support this type of multi-threading. So we'll see an example of that. Let's go to the first example, but before that, there are 2 steps I would like you to do, and it's written also. You can copy the commands from what's it called, the Discord. Thanks. You can copy those things. I've prepared. I prepared a few modules, but most of the modules were already there. But you need to load these modules in your home directory. And for some reason also, and I need to look a bit into more detail, but yesterday I was just managing this, making it all work in the HPC, but I need to set the Python path, or unset, let's say, the Python path, because there are too many legacy things. By loading all these modules in my Python path, that there were some inconsistencies. So I want to get rid of all the Python path from the past, and I want to create from scratch, like with a clean build, the new modules I want to load. So here, you first load these modules, and then you install the pyjeo wheels. The pyjeo is, as I mentioned, it is based on the C++ dynamic library, and so an SO files in Linux speak. I create, but on top of that also there is already, I created a wheel where these dynamic libraries are incorporated. So by installing that wheel, you have already those dependencies of the dynamic library. And then there's a second, the pyjeo, the actual pyjeo, which is actually the wrapper in Python, that you need also to install, and that's in this the second wheel. Has anyone already done these steps? Are you at this level already?
So first load all the modules, then line by line, second step. Keep going.
Giuseppe maybe can help if there's anyone of you who needs some assistance. Okay.
It's only steps 1 and step 2.
Okay, maybe. Well, I can copy it. That's a good point. Let me copy it. Yeah, but okay, it's easy that you don't make mistakes. That's a good point. Thanks. I'll do it now. Coding. Why isn't it working?
Be sure that you enter in the Python requirement. So be sure that your left prompts directly there.
So we will, the two exercises, the first is called this calculate NDVI. The second is called, sorry, no, I made a mistake. Sorry, this needs to be pi. Don't execute yet. Too late, probably. Shell pi, shell pi, shell pi, shell pi. Sorry for that. So there's a shell script and a Python script. As you remember from yesterday from Giuseppe's course, there is the shell script where the slurm commands are defined in the beginning, and then there's the actual command, and the actual command will call the Python function. So there's, for that reason, there are these two files, a shell file and a Python file. No, again, good, there are some people that are awake here. So we are it should be extract parcels, right? Yes. No, it's not recommended. I mean, for later on, we will create a plot. So if you have one available, it's good, but you don't need it for this part here. You work in the Python script, and only at the very end of the last exercise, it would be good if you have either some on the command line, you can do some Python, create a Python script in your editor, or if you have, even better, if you have a Jupyter notebook for that purpose, it would be good. Yes. No, not for my, I don't think so. Indeed, no, you don't need it. This is just for presentation purposes. Yeah, you that are well awake, can you check, please? Good. Okay, I still have to copy it, I guess, right? And also I need to get rid of those commas also, so I can do that as well. Oh no, how did they did that? Sorry, so it's someone has the correct thing already, or? Sorry? Okay, let's see.
The bash code for calculating and extract parcels. Yeah.
Are we so far? Yep. So let's go to the surf computer. So you have these 4 files here, 2 Python scripts, 2 shell scripts. Let's see what's in that calculate NDVI shell script. This should be very similar, if not the same, as you've seen before with Giuseppe yesterday. So we define some typical Slurm variables. We call a single node, a single core with a maximum, way too long, but 1 hour of processing. And we are producing a standard error and standard output in our home directories under std out and std error. We are also creating a data directory in our homes. We load the modules and we set the Python path or unset the Python path. We activate the virtual Python environment you created before, and then we call the Python script with the following arguments: input, output, and then you see, so the input is a Sentinel-2 composite I created before, so it's already available in this data directory. I can show you here maybe some comments on it is this S2 composite. It has 2 spectral bands, a red band and a near infrared band. So we call him in the Sentinel-2 nomenclature the B04 and B08. The spatial region is the entire region of Flanders in Belgium. And it's a maximum NDVI composite between July and August of 2021. And then interesting, as we saw before, you can open an image, a very large image. For example, we were talking about this VRT. Let's say you have 1,000 files distributed in your file system, and you created a virtual file that is combining all these 1,000 files, treating them as one single file. You can open that one single file, but of course doing that would be way too much to have in memory. So what you can do to save your memory, not only to save the memory, but also to prepare for typical parallel processing, you can say, I want to divide that images in tiles, and without having to do that manually, like you were seeing yesterday, you could do that by creating a virtual file again. But in pyjeo, there is this mechanism already implemented that when you say, I want the tile total, sorry, this is wrong. I want a tile total of 64, and bear in mind the tile total here, the way I program it, it has to be a square number. It has to be 8 by 8, 4 by 4, which mostly is not really a problem. But so you create a tile total. I want to divide it in 64 tiles, and I want to load only the X tile. The tile can be from 0 to 63. And then only that portion of the virtual file. And of course, if you have already a virtual file, it's very efficient because it will only load those real TIFF files, not the virtual, but the physical TIFF files that are needed to open it, and you will only load that image, and that can then be processed in on the cluster. And also the nice thing here is because we are working with these style indices that go from 0 to 63, it's very easy to link that to a parallel processing because the parallel processing typically has also some kind of index that the orchestrator can then send these tasks to the cluster and the individual processing nodes. So it will already automatically cut your image, and then you can just call that batch script. So let's see here what's this is actually what we see here. The tile total is 64, and I want tile index, for example, the second tile with number 1 or number 0. And you can change that in your particular script. You can do whatever as long as it's above or equal to 0 and smaller than 64, so maximum 63, and it will process that different tile. So let's call it. Let's see what's happening. I submitted a single job. And you remember maybe there is this oh, it's already finished. Oh, is there something wrong? Let me check. It's still processing or what? Is it being processing for some of you? It is. Maybe I'm all in the. I got to get the list of the priorities, and I'm the last one that is able to. Huh?
Bash script. You should put also the CPU in the S. Like here, C 64.
Where?
I think.
C.
Yeah.
64.
Because you're using 64 tiles.
No. Okay, but I'm doing it. I'm just example for one.
For example, one core.
Yeah. 1 core for 1 tile, and then you can do more if you want. Is it finished for some of you? Do you have a result? And it works? Okay. Mine is still in the queue. So now you have probably seen with Giuseppe also how to launch several jobs. And you want, of course, to adapt the tile index according to the number of processes you launch. So that's how you do it then for the full 64. I'm not sure if we are doing it for the 64 with the whole class. Maybe it's a bit too much for, but
You put less.
you can. Yes, yeah. So you can do that to. I'm not sure how much time we still have, but yeah, we can.
Script.
Bash. Just batch. Yeah, for everybody, remember, it's like yesterday. You need to change this one,
Yeah.
the standard error, standard output to your home. We are going to use perfectly the same folder than yesterday. So just change this one.
Yeah, I'm used to the. Microphone. Okay. Was everyone able to execute? Yeah. Okay, good. Yeah, one comment. What I did, I said there's some. It's semi-automatic. The tiling. So you have the tiling. Let's look what. In this Python script. As I mentioned, when you have this tile index, it is here. You read only the portion of the image, the portion of the image that is needed. And then that is taken care of. What is not taken care of, because you will only process that image, but the output file name needs to be adapted. So if you say, I want output file name as I did here, just the name of a TIFF file, then it needs still to be adjusted. So for the tile index, and that's what I've done here manually. I say the output file name the user has provided. Let's take only the name, not the directory and not the extension, not the suffix. Append an underscore, my tile index, what is actually being computed, add an underscore for the tile total so that I know as a user how many tiles there were, and then append the suffix. So if I was putting like image.tiff, it will be image underscore 0 underscore 64.tiff. So this is done manually. At the end, when you processed everything, you will have 64 tiled images. You need to still combine them, but that is done easily by a GDAL VRT, build VRT command. And you don't even need to create a physical GeoTIFF file for it, because you can leave all the tiles if you want and have the VRT file. Okay. If that's all clear, let's move on to the next exercise. Let me take back the. Let's go to. Here. So we have done this, a few tips first. Oh, you've seen I've used this arguments module in Python, which I find very handy, and also it's better than working with hard-coded paths. So you can have this, and I think it's quite. You can copy from this script for your later thing if you want, but I find it quite useful and much more readable if you are using this argparse. I have also included a verbose mode. It's very useful to know what's ongoing, especially if you are debugging. If you don't want all the cluttered information, you can just remove, or you can just not use the verbose mode. So that's another tip I would like to give. Write to temporary files like we've done here. And then at the end, you see how it's done. Also, you can copy that as well from this script, how to use temporary files, and then copy later on to the final destination. As you might remember from Raymond's talk, it's always good to use the Scratch because it's much faster and it's much more reliable than using a distributed file system. Clean up temporary files. In this case, I don't think it's really necessary because I think it's automatically done if you use the temdir, but otherwise in our system, for example, users are responsible to do it, so you don't forget. And so whenever possible, this tiling mechanism, I think it's very efficient for parallel processing. You will hardly find any better parallelization speed up than with this. With that, let's go to the second exercise. And so this is a different type of parallelization, as we will see. In this case, we take the same region, Flanders region in Belgium. It's the same composite. It's a composite from Sentinel-2, and we want to extract the information in that raster data, but within looking at the data within some parcels. So we want to overlay some polygons, these 35,000 polygons over that raster image, and extract zonal statistics from within those parcels. And we want for the zonal statistics to calculate the mean for one parcel, the standard deviation for one parcel for that specific band we're interested in, and also the sum. There's some other statistics you can do, but in this case we're interested in those three. And this is quite computational extensive type of processing, because you have to go through all these parcels and extract some information, do some statistics. And here, so the multi-threading mechanism was implemented in pyjeo, and actually the way it's done is you go through the different polygons, and each polygon is distributed to a different core. So you will use as many cores as are available or as you define, and each, as the polygons can be treated independently, you can very efficiently use this type of mechanism. So here, what we will do is adapt this C1 to any number to 8, up to 8, because I think the surf don't allow us to go over 8. Is that correct, Raymond? No? We can go. But I went. Let's for now. Let's do it only to 8. Don't stress the machine too much. And what I would like to also observe, or I want you to observe, is something we call Amdahl's law. There's a debate. It's quite old still, but there's a debate if it's accurate or not. But I think as a general rule of thumb, it still applies, and that is an equation to calculate the speed up of your program. You can imagine if you, as I mentioned, to make use of this parallelization principle, you need to take that into account in your programming. You cannot just say, I want to parallelize all the things if your program don't, if I didn't implement that every polygon has to go to a different core, and if everything is done sequentially, there's no use of assigning more cores. So you can imagine that not everything, even with the best will of the program, you cannot parallelize everything. For example, opening a file, closing a file, and some other operations are not easy or not possible sometimes even to parallelize. So there's always a portion only that can be parallelized. And if we call that portion P, this formula will show you how much speed up you will have. And speed up is typically like 1 to 2 or 3 or 4. Speed up of 2 means with using 2 cores, you can have the double performance. It will be double as efficient in processing time as if only 1. And that will mean the parallelization is 100%. So this will never be the case. So let's see what happens. So I just have this simple formula here for different parallelization going from what did I use here, from 10 to 90%. If I have 90% here, I can have a speed up of 3. So it's only 3 times as fast as a single core if I'm using 7 cores. And even you could think, how is this possible? I have 90% of parallelization and still I'm only able to get a speed up of 3. That is because even that single sequential part can never be optimized, and it's all cannot, even if you have, like, the best you can do is you have an infinite number of cores, and the parallelization part will be immediate, but still the sequential part has to be done sequentially. So what we would like to see here, what is if you have something that you parallelize, you want to see how much speed up do I get, and how was it programmed, so you can actually estimate that portion P for that particular program by just trying to get this figure, and your plot will be somewhere in between, maybe here, and then you can see, okay, I'm here, I follow this path more or less, will never be, because this is a theoretical formula, of course, it will be somewhere here, so you can calculate what type of parallelization you would have. So let's try to do that in our example here with the extraction. First, let's see what I have put. So I have here put here 8. I can leave the 8 here as a maximum. I will have 8 cores. And what I did in the Python script, I will first get rid of this. I will not do the verbose because I'm only interested in the time. So I'm doing this extraction, as you see here. I'm opening my GIM image. I'm opening a vector file, and I will do the extraction by calculating these with, as a rule, the mean, the standard deviation, and the sum. I will output to memory here, because I'm not really interested in having the actual file, so no output. But I will see how much time it will take to do this extraction. So I'm calculating the time here by start time here, daytime now, and then here calculating the difference between daytime now and the start time in total seconds, and I output this number of seconds. So you'll see for 8 cores how long it will take. And I'm just also editing this shell here, so because I will not put this verbose, I will just get rid of that. Now, and let's execute. So maybe you're familiar with this watch. You can check the queue with this SQ minus job and then your job number, but it will immediately go away because it's a single command. By putting watch before that command, you can see what's happening in real time. So you see here that it should be running.
Peter,
yeah,
one comment. So if you do SQ minus U and then your username, you can monitor all your jobs at the same time. And you also don't have to give the job number.
Okay, so here minus Q.
Minus U.
Minus U.
Yeah, and then your username. So do you course teacher something or do you course student something?
Okay, very good. Okay, thanks. Okay, let's see if it's is it actually running. Extract. Let me also do it for a single core. So here you see my two jobs are running for 1 minute already. And one should end more quickly actually than the other. But maybe I edited too early. Not sure. Okay, one is finished and the other is still ongoing. So if I look in the standard out, I see in this case, I was running with 8 cores. It took me 44 seconds to extract these 50,000, 53,000 polygons. The other one is still ongoing, where I took only 1 core. So what you can do now is you can start the different processes. So I'll do another one, taking like, let's say 4 cores now. Start it again. It's not started yet, but so we still have the 1 core process running, and I have launched one with 4. If I do that for all these and number of cores, I will get in my output all the times, and I can plot these in my matplotlib and then see how much my program was able to parallelize.
Also, Peter,
Yes.
if you ever want to find back how long your job's used, there's the SACCT command. So the S slurm accounting command, and you can find back how much time it took.
And you find the different times, like processing time, user time, and all this information.
You can find a number of things, and there's lots of options to modify the format. So it gives lots of information, but
very
good
good
historical information.
Okay, thanks. So you can also just launch all of them and then go back to those. So that's very interesting indeed. Another thing I want to mention here, and this is a bit difficult. Like when you want to do this type of checks and especially if you want to publish some results on parallelization, you have to be very careful because we're working on a remote machine. We don't even know which machine it is running on. So it could be that one core you're using, which has been distributed to, is a totally different machine than another core. I don't know in this case how it is, but you have to take care of that. Or maybe the network is much more heavily used because we're in a classroom and everyone is using it than in an empty, in a dead moment when nobody's using it. You're doing it during the night. So you have to use these type of numbers very cautiously. So here it's good to have an impression to, of course, we are expecting that the 8 cores will be faster than running a single core, but you have to take it with some salt, these type of things. So if I'm going back to the 43, 55, 54, you see this time was extracting the polygons with 8 cores, 44 seconds, and this is with a single core only, 160 seconds. So it's at least it's a good thing. We see that there is some speed up. That's the good news. How much speed up did we obtain? Now it's a matter of trying to fit this. If we have done it for all the 8 different cores, we can more or less estimate how much speed up we gain. But at least we see if I'm not sure if we can go even, because as you see in this figure here, of course, it all flattens out. We are not getting, I mean, if I would plot here 100%, then it would, of course, be linear, but there's no program that actually can obtain that. That is really a linear type of speed up. The lower you get, the more flattens it. So if you have this type of parallelization, don't try to use like 1000 cores. It doesn't make any sense. So the better parallelizable it is, the more cores you can use, but there's always some flattening. So you can also see here that after 8, you can try to get many cores, but what's the actual use of doing that? So it's quite an interesting way of looking at things and to see what the optimization is. What I've done once, and there's a paper also on that, is for this type of processing, I was also comparing for this particular program, what's the efficiency of trying to tile your image? Suppose you have 1000 cores. You could tile your image and you can multi-thread your extraction. And where is the optimum? Because you can, of course, tile it very little, but as I mentioned, there's in the tiling at some point you're reading a single pixel, but it's very inefficient. And of course, it also depends on the size of polygons. If you have a big polygon, there's no need to read a single pixel. You need at least to have that size of the polygon. So you can tile your image, but or you can do the multi-threading. But doing a lot of multi-threading, getting all the 1024 cores, using that all for multi-threading, you'll see it will be very inefficient because we're in the flattened line here, and you can not use then those tiles for tiling up. So there's some kind of an optimum by tiling and by using multi-threading that will be somewhere in an optimum mode. And of course, it depends very much on your specific application. But these are things that you need to keep in mind. Maybe there's already some other. Let's see if it's okay. All is done. That we can do the final. So when using, you see already the flattening happening. When using 4 cores, the processing time was 61 seconds. You see 1 core, 160 seconds, 4 core, 61 seconds, and having an additional 4, I can reduce it to 44 or 45 seconds. So the gain is not that much anymore. So from 1 minute to 44 seconds, and I need 4 cores of it. So it's much better to go from 1 core to 4 cores. I can have a lot of speed up, and I could maybe use the other cores for tiling my image or doing some other things or leaving it to my colleagues. So that's a good thing. Any questions?
I was just curious about how your daily work as do this parallelization. So will you, every time you do the process, will you also do the engineering to see that how much core is optimal and then go to deploy your code in the production line? Or we just like, because you have so many different concerns, right? How many cores you can use, how many RAM you have. And this is might be also important for your work.
Yeah, sure. In practice, I take as much as I can. No.
Yeah, me too.
No, I think no. It's. I think it's good to do these things to be aware.
Makes me very unhappy.
I think it's good to be aware. I mean, as you see here, there's no point of trying to get as many cores as possible. So I'm not doing this type of exercise for all the. But at some point, you do some prototyping and some testing, and especially what is more even more important is to know the program also in the memory footprint, because if you need a lot of memory, like also in a serve, you need to scale up the number of cores just to be able to get your memory under control. So that's there in practice. There's much more than just trying to speed up as you would like. So indeed, in practice, you take these things into account. Am I doing all this type of analysis before? No, but you have to know more or less what you're doing. And like I would say, if your problem can be solved by tiling, it's very hard to outperform it with multi-threading. In this case, it is quite optimized, the multi-threading. It serves some, you could do 1, 2, 3, 4, up to 8, but even 8 is too much, I think. 4 cores would be ideal, and then try to, as if it allows to do the tiling. Because the tiling is an embarrassingly parallelizable type of problem. This is not, because the multi-threading is never embarrassingly parallel. It's close to, because you can divide the different polygons to different cores, but there's always an overhead. So yeah, if you can do the tiling, most of the time it's the best practice you can do. Yeah, you will.
So, sorry, do you have any benchmarks on at what point you want to start tiling instead of going parallel? Because when you have like large amount of RAM, you can do a lot of processing on the RAM.
Yes, but I think let's suppose you have a 1 terabyte of RAM, and you can say, I don't need to tile. Of course, you don't need to tile, but it will still take you much more time than if you would tile. So it depends on how heavy your processing is. If it's like calculating an NDVI, would I tile if it fits into memory? Probably not. If it's like a heavy processing, doing classification, pixel-based classification maybe, or some other things that require more time, I probably will. So it depends on the problem. And also taking into account that, I mean, this memory, is it a shared environment? Are you sharing that memory with your colleagues? Or do you have one giant computer on your desktop that is only for you? That's also differently, because every resource that you're taking is less for another one in a shared environment also.
So maybe just to add there, so there are profiling tools available from the different vendors. So Intel, NVIDIA, AMD, they all have profiling tools, but they do require quite a bit of in-depth knowledge to understand whether you're IO bound or memory bound, or how efficient you are actually using the CPU. The other thing that is maybe good to mention is that in the coming years, the memory per core is going to decrease starkly. So we're going to head towards many core CPUs. So right now, maybe you have 64 CPU cores on a CPU. We're going to go towards 196, 192, maybe even 256. The memory is not going to increase with that. So right now you have 8 gigs maybe per core if you're lucky. You're going to go probably down to 2 or so in the future. So memory management is going to become much more important. The other thing that, of course, will also be outside of this course probably today is that optimization for the specific processor or GPU that you're working on can also drastically change things. So if you compile for an AMD or you compile for an Intel, and they have to use specific libraries, and that can mean factors of 2, 3, or 4 different in certain ways of doing certain transformations like Fourier transforms. That all requires fairly in-depth knowledge, and whether or not it's worth it for your specific problem and your time to result is something you have to decide yourself.
Yes.
Yeah. No, just one point that I would like to check with you. So we are implementing basically kind of both. So we have, like, in each node, we have about 1 terabyte. You were pretty precise in your example. So, and our strategy, it's basically filling the RAM as much as possible, because once we compute something, for example, we prioritize that, and we know that, okay, other person will not kind of use the nodes. So, but one thing that we notice is we are also parallelizing the reading. So we do per tile and we do the reading parallel, because with the GeoTIFF, you have this decompression algorithm. So, and if you read, like, I don't know, as much as image as possible, like 96, you will take some advantage as you show. But once we have this data in RAM, we also do this multi-threading to, for example, we split internally the tile. If we compute the NDVI, you compute the NDVI also inside of the tile with multi-threading.
So the tiling is done multi-threaded?
No. Yeah, so because we read the data, like it's 1 tile, I don't know, 4,000 by 4,000 pixels. I will kind of show it on Friday. And now we just need to compute the NDVI. So internally of that chunk of data that we read, we have a multi-threading approach to compute that. But one thing that we notice is, because with Python, you have this problem with the GIL. So you can't reuse efficiently threads. So we move this computation to the C++. I think it's what you are doing here.
Here it's also in the C++ part.
Exactly, because in this case, you can really take advantage. So my question is, what functions you have that you really explore this multi-threading approach on the C++ side? Because if you go for the Python and you want to do this, first, there's no multi-threading Python, you know, and if you have multi-process, you need to share the process. They don't share the same memory in space. So you need to move a lot of data. So what we are doing now, it's basically moving most of our core functions to C++ to take advantage of the multi-threading that you use it here for the polygons. Yeah. But for the raster work, that's
yeah, indeed. So yeah, good point. Here it's the same, because I'm coming from the C++. I did all the multi-threading already in the C++, and the Python part is initially how it started. It was only like a wrapper. It's only to call the functions, nothing. However, gradually, I saw that if I want to, it's much more easy to add functions at the Python level because you don't need to recompile a thing. So sometimes what I do is when I need to add a function, I see if there's something available, and then I don't even have to adapt the library. If something is already available in NumPy, NumPy is also multi-threaded already in the C++ level. So if I can call the function in NumPy, then but in this case here, indeed, nothing is done on multi-threading at the Python level or parallelization. It is indeed and what are the things that are implemented? One of the things, for example, is there's a reason of this because I natively it was just my memory is just an array. And it's just by doing these tricks to go to the API of NumPy that I can represent this in a NumPy array. But at the end, it's just an array. And it's sometimes, if you need to work on several areas in your array, it's not that easy to parallelize if you don't go sequentially for the multi-threading part. So apart from what I showed here on the multi-threading for the polygons, what I can easily do, and that is one of the choices. So I say I did for the spectral. So I have a 3D image that is contiguously in memory, but I have on the spectral bands, I have a different part in memory. So I have this 3D cube here in memory, contiguously, and then another part here for another band, another part there. And that is very efficient for doing multi-threading because I can work here on one band. So if you want to do a pixel-wise or some operation on the different spectral bands, then I also include multi-threading more easily than doing it in the Z dimension of the planes, because then you're fiddling around with the same memory. So here, that's one of the reasons of the how it was designed also. I'm available for questions, but I'm finished. So we can go for lunch. We can do whatever you wanted. You were a bit afraid of the time, so perfectly on time. I think we have even before. So, but unfortunately I need to leave this evening. So I'm a bit unable to follow the other very interesting things that I've seen like this morning. So or like sorry, this like yesterday. A pity, but I'd like to be in touch with you, and whenever you have a question or so, don't hesitate to either to contact me now or via email in the future.
Yeah, thank you very much, Peter. I think it's a nice tutorial. It's really what I really like when and to see when the geospatially aware people make the libraries in Python, so that makes me more secure when I use the tools, and also this span easy connection to the X-arrays and NumPy, so that really makes a lot of things easier in Python for many users. Maybe it's important to note that all those tools were actually existing before X-arrays, so or maybe at the same time, yeah, you started. So
well, maybe more than 20 years ago, I think. So.
Yeah, but your Python library, I think.
The Python library, that's maybe from what is it, 2016, I think.
Yeah. So, but I think it's very interesting. Also, maybe it's also relevant for PanGeo people. I think they rely a lot on X-arrays. So maybe Anne can also reflect on that. But yeah, thanks a lot. I think we shall stick to the schedule. Yeah. So maybe we can still work half an hour here, and then have a lunch in half an hour. Yeah, so then yeah, either you can post some questions or discussions to Peter, or you're just working on your own data, and then in half an hour we have a lunch.